Hello, everyone. This is Jinyu Zhou from Apple FoundationDB team. Today, I'm happy to present our paper, FoundationDB, a distributed unbundled transactional key-value store. This is a joint work with amazing collaborators from Apple, Snowflake, and antithesis.com. This talk is organized as follows. I will first describe FoundationDB and ACID transactions, its design principles. Then I will dive into transaction processing and recovery of FoundationDB. After that, I will talk about the simulation testing, related work, and finally, the conclusions. So what is FoundationDB? It is a distributed key-value database. Different from NoSQL databases, FoundationDB provides general-purpose multi-key transactions and also maintain read-or-write semantics. FoundationDB provides point key APIs for read and write individual keys. It also provides range-based APIs for scans and deletes. The deletion in FoundationDB is efficient because we use tombstones as storage layers. Keys and values are binary strings on top of key-value databases. They are layers to provide high-level data models, such as relational data in FoundationDB record layer, or MongoDB document model as in FoundationDB document layer, or graph database such as Genus Graph. FoundationDB has been used in production in Apple, Snowflake, and other companies, storing critical data. Why ACID transactions important? Let's consider key-value store systems that provide eventual consistency. In this example, at time t1, if you write some data to the database, and at a later time t2, if you try to read the data back, there are three possibilities. One possibility is that the database says the data is not there because the data is not fully replicated. The second possibility is that a stale copy is returned for the same reason. And the third possibility is that you read the data that was written at time t1. As you can see, eventual consistency makes it hard for applications. In contrast, strict serializability guarantees that at time t2, you can always read the data you written previously at time t1. So this is much easier for applications to reason about concurrency semantics, which makes the developers want to adopt a strongly consistent key-value stores. FoundationDB provides a strict serializability, and we use the timestamp ordering technique. Each transaction happened at a certain time, and the later transactions will always observe previous transactions. So in this example, if the first transaction commits at time t1, then the second transaction at time t2 will be able to see the committed data because the timestamp at t2 is larger than the commit timestamp at t1. The transaction model in FDB works in this way. When a transaction starts, it first gets a read version from the cluster. Then all the reads and writes happened at this version. At the commit time, the transaction is assigned a commit version. To the outside observer, this transaction happened at the commit timestamp. For read-only transactions, it happened at the read version. So in the example here, at time t2, the read version is no less than the committed version happened at t1. Then FoundationDB guarantees read will always see the data written at t1. There are four design principles in FoundationDB. The first one is to divide and conquer. We try to separate the whole transaction system and the storage system so that we can scale them independently. And we also further divide the transaction system into smaller components. The second principle is trying to make a failure a common case. Instead of hiding a failure, we tried to make a failure a very common case. Any component failures in the transaction system causes a transaction system recovery that will always be handled by the same recovery logic. We tried very hard to make this recovery very fast so that we can sustain a high availability. Finally, we use simulation testing to improve code quality. Let's see how this divide and conquer design principle is used. FoundationDB adopts an unbundled architecture, which decouples the control plane from a data plane. The control plane manages some critical metadata using a disk of pixels. It also manages some cluster-wise operations, such as coordinating data movements. The control plane is decoupled from the transaction processing, so its availability doesn't affect the transaction processing. The data plane performs the transaction processing and also serves client reads. FoundationDB targets OLTP workloads that are read and modify a small number of keys, and have a low conflict rate. The data plane is divided into three components: a transaction management system for in-memory transaction processing, a log system that provides write-ahead logging, and a storage system that serves reads for the client. These three systems can be independently scaled. If any component fails in the transaction system and log system, a reconfiguration process is performed so that the system can recover to a clean state. Now let's see the life of a write. During commit, a client transaction is sent to the transaction system, which consists of three roles: a proxy role for accepting client requests and coordinates transaction commits, the sequencer role for handing out read and commit versions, and is a global singleton, a resolver role for performing conflict detection using optimistic concurrency control. After a proxy receives the commit request, the proxy first sends the request to the sequencer for the commit version. The sequencer increments commit versions at a rate of 1 million versions per second. Then the proxy forwards the transaction data, specifically the read and write conflict ranges, to resolvers. After all resolvers accept the transaction, the proxy will send the transaction data to the log system for persistence. Once all the log servers have made the data durable, the proxy reports the commit versions to the sequencer and then reply back to the client. In the background, the transaction data is shifted from log system to the storage system for persistence and serving subsequent reads. Essentially, storage servers keep MVCC data. Because data is durable at log systems, storage servers can batch apply data to disks. For reads, as we mentioned earlier, the transaction will first get a read version from the cluster. This is done by sending a request to the proxy, and the proxy asks the sequencer. The read version is the largest committed version known to the sequencer so far. Then the client can issue reads to a storage server together with this read version. If the data is available on a storage server, the data is immediately returned. If it's not available because of a delay between the log servers and the storage servers, the client will wait a shorter period before issuing a backup request to a different storage server. Hopefully, the read can be served there. In the rare cases that a storage server doesn't have the data for a long period of time, the client will get a timeout error and can restart the transaction. This is a measurement from 1 hour production cluster. In a period of 12 hours, the average latency between the storage servers and the log system is only 3.96 milliseconds. So most of the time, client reads can be served by storage servers without any wait time. For transaction system recovery, as I mentioned earlier, we are not trying to make mask failures. Instead, we use reconfigurations to recover from the failure and it's very important for the recovery to be very fast to improve system availability. In FoundationDB, there's no checkpoint and no redo or undo log processing during the recovery process because the recovery is very simple. We just need to decide the recovery version, and then the processing is the same as the log forward path. In terms of roles in the recovery, proxies and resolvers are stateless, so they recover without doing any processing. For log servers, we may need to heal replication degree for the last few seconds of data. This is done by copying a small amount of data from the old log servers to the new log servers. The details are in the paper. For storage servers, because they have semi-committed data that may need to be rolled back during recovery, the recovery transaction will tell the storage servers the recovery version. The MVCC data on the storage servers is kept in memory, so their rolling back is very simple and efficient. From our production cluster measurement, the median recovery time for recovery is about 3 seconds, and the 90th percentile is about 5 seconds. Such a short recovery time ensures high availability of the transaction system. One thing to point out is that because the reads go directly to the storage servers, they are not affected by the transaction system recovery. The cause of these recoveries include automatic failure recovery from the software or hardware faults, software upgrades, database configuration changes, or the manual mitigation of production issues by the SRE team. One of the unique features of the FoundationDB is the integrated simulation testing. In fact, the founders spent their first year in writing the simulator before writing any database code. The simulation testing is both deterministic and randomized. The whole distributed database cluster can be run inside a single process. This is possible because we use an actor-based programming model, where each FTP process is just a bunch of actors communicated with a message passing. All the randomness from the environment is abstracted, including disk IOs, network, time, and the pseudo-random number generated. The simulator also incorporates a fault injector, which can inject machine, rack, or data center failure stop errors, as well as network and disk behaviors, such as delayed or reordered message deliveries. Programmers can use Bugify in the code to make rare states and or events more common. For example, return an error for a function or an RPC call. The simulation also supports application workloads, which can exercise the database with the transactions or invoke internal database operations. Workloads can be composed to construct different test cases. Finally, we use swarm testing to test the database on the various configurations. The testing framework is now open source on GitHub. The benefits of simulation is tremendous for FoundationDB. It reduces latency to find bugs because we can arbitrarily make the simulation time faster than the real time. Additionally, we don't need to set up the real cluster for testing the database. The simulator testing is embarrassingly parallel. We can just add more processes to boost the number of tests. Simulations also reduce the debugging time because we can arbitrarily add traces to the program code and it's guaranteed to reproduce the error. We can use the GDB to stop the simulation and look at the program states. This has been proven to be very useful in our deployment workflow. In multiple times, we made radical changes to the system and we discovered problems very easily with the simulation, which is critical to improve the software quality. In Apple's CloudKit, FoundationDB has been used for more than 500,000 disk years. So far, we have not found a single case of data corruptions. However, there are limitations to simulation. For example, performance bugs or the third-party libraries, such as SSL libraries, are not in simulation, so we cannot find bugs in these cases. The unbundled architecture has proven to be very flexible for cloud deployment. It also makes the system very extensible and performant. For example, if we find there's a performance issue in a row, a common pattern we used is to decouple the row into multiple rows. In the past, we have separated data distribution and the read keeper from the sequencer row into two separate rows. Faster recovery is also proven to be very useful in simplifying software upgrade process. The traditional wisdom of software upgrade is to perform rolling upgrade, which can take hours or days. In FoundationDB, we always do an instant cluster-wise bounce of our processes. So the upgrade is just the same as the recovery process, which happens in a few seconds. It has also been used to perform database configuration changes and also to mitigate production incidents. In terms of related work, FoundationDB is related to a rich body of previous work. Many key-value stores do not provide ACID transactions. FoundationDB uses optimistic concurrency control and MVCC to support strict serializability, which is different from the pessimistic concurrency control commonly used in unbundled databases. The recovery time in FoundationDB is optimized so that redo and undo log processing is not in a critical path. And we use the simulation testing to improve the software quality. To conclude, FoundationDB is a distributed key-value store designed for OLTP cloud services. The big ideas are, first, we decouple the transaction processing from logging and storage so that we can scale the transaction system and the storage system independently. Second, we use OCC and MVCC to achieve strict serializability. And finally, we use the deterministic simulation to improve the software quality. FoundationDB is an open source project on GitHub, and we welcome any contributions from the community. Thank you for listening.